Thank you very much. It's a great pleasure to be here. I'm going to try to tell you about efforts to sort of move QMC beyond sign problem free to tackle some sign problem systems. What I talk about will try to, well, quite a bit of the content is in this write-up lecture notes here, so that might be useful. And I already see that people are doing fantastically in terms of asking questions. So that's great. Interrupt me. Concrete systems, if you use the Hubbard model, it's kind of a cane to think about when I'm saying stuff, make it more concrete. I think that will be useful. And the later part for tomorrow, I'll try to give you a sense of how to do real materials. For that, the hydrogen chain is a good system to keep in mind. So this is a little illustration of that with the orange yellowish points or protons that are fixed on a line. And then the black dots are electrons. So think about this system, how you would model it, how you would understand its physics. Sort of simplest thing in the limit of a large separation of protons. It's like a one-dimensional Hubbard model. But as you compress this, it becomes realistic how you think about that problem. I think with these two, you'll be able to put the context, what I'm talking about in reasonable context. So outline. I'm going to give you an introduction. This introduction is kind of a skewed view, but I want to kind of talk about a mindset, how QMC can help tackle many more problems. I think we already are doing a fantastic job with the codes, with ALF and so on, coming on board. But we'd be able to do more if we take a slightly different mindset about the sign problem. Now, this is the second time I'm talking about this part. Unfortunately, it's also the second time that some of the senior people here will be hearing about it. So apologies for the repetition. And then I use the finite temperature version to try to connect with what you've heard about, to talk about the sign problem, understanding how it happens in this framework, and why it happens, how it happens. And then that will lead to an introduction of the constraint path framework. I'll use the finite temperature version to do these two to understand why, and then it'll come more naturally why we can think about a constrained framework. And then this will be more brief, talk about ground state. Historically, this came first, the ground state came first, but I'll introduce in the ground state how you think about real materials, how you think about Coulomb long-range interactions and multi-band type of interactions, how you decouple those, and a phase problem happens, and how you deal with the phase problem. And in particular, the kind of this part is geared toward, this is the hydrogen chain I mentioned, computation in real materials, how you formulate the problem and how you deal with the phase problem. So this has already been in existence for a while with a lot of applications in quantum chemistry that I'll briefly touch on, and then ab initio solids. So you're familiar with this, the QMC doctrine in terms of dealing with correlated models. It's numerically exact. You run your ALF calculation, you expect to get numerically exact result for that particular Hamiltonian or that particular physical set of parameters. But there is a sign problem. Right? And this is, because of this, QMC is often fairly casually, I would say too casually, dismissed as a viable approach when the sign problem is present. And this is, I just did a search a year ago. Randomly, the sort of more prominent A paper came up that says quantum Monte Carlo methods suffer notoriously the so-called sign problem, negative probabilities. There's not a whole lot of follow-up. It basically says, well, therefore, you don't have to consider this type of calculations for these problems, right? That's kind of the implication. This is also a year old. Maybe ChatGPT is smarter now. A year ago, when I was preparing this part, I asked ChatGPT, I tried to lead witness. So I asked a question that sort of went that way. Why is quantum Monte Carlo not suitable for studying the Hubbard model? It went on, give me a long diatribe quantum Monte Carlo methods are powerful, blah, blah, blah. And then it says the primary reason why quantum Monte Carlo is not well suited for studying the Hubbard model lies in the sign problem. Somewhat true, it went on, long things. And then it says other numerical techniques, dynamical mean field theory, DMRG, have been more successful in tackling the Hubbard model's challenges due to their specific strength in dealing with strongly correlated systems. In summary, the sign problem in quantum Monte Carlo methods makes them unsuitable for studying the Hubbard model efficiently and accurately. This is not true. Right? We do struggle in dealing with the Hubbard model, but quantum Monte Carlo not more so than any other methods, right? It's a grand challenge, but this is sort of a narrative that I think just got cultivated, but maybe our community is somewhat responsible too. Peter, you had a comment.
To that effect, I just have to comment that ChatGPT is constantly being updated. So it's a year old.
So, as I said, yeah.
You should check ChatGPT
Yes.
now. Maybe our community is already fixing this, the response.
For my purpose, it'd be interesting, somebody could do the live check. As I said, this is from a year ago, these slides. It's when the first time some of you saw this, and it's on the first time I talked about it. This is number 2. Somebody should check, but I doubt the community's view has changed, okay? But the ChatGPT answer might have changed due to recent things, but I think this view is long lived. And I hope it'll change soon. Okay, so this is incorrect. QMC has been instrumental in understanding the properties of the Hubbard model and its connection with high TC. This is, of course, ongoing, and we don't know very much. We know embarrassingly little. But QMC, in what we know, has played a key role, right? This is, I'm giving obviously a very biased sample, but I just want to make the point. So the biased sample has a lot to do with work I've been involved in. This is old paper dating back more than a decade. It using QMC, it's predicted filled stripes in the Hubbard model. This did not stick, right? Probably having to do with this sort of systematic views. And then 2015, the Simon's collaboration on the many electron problem launched the first paper, first benchmark, where QMC again played a key role in putting out a lot of the benchmark results that are currently used. And because of that, for example, a follow-up paper using 4 different methods where AFQMC played a key role here again, established stripes in the doped Hubbard model ground state. And then this paper, 2 methods, DMRG and AFQMC, showed that in the pure, so-called pure Hubbard model, there's no superconductivity in the ground state. And now this paper that just showed up showed the coexistence when you have a T prime term, same set of work, 2 different AFQMC and DMRG, showed superconductivity in the ground state for both electron doped and hole doped side with partially filled stripes in coexistence. So some of the biggest successes from QMC in condensed matter and beyond have come from sign problem-free models. You've heard examples. You just heard one from Peter. And dealing with sign problem, sign optimization, finding models, model engineering, finding models that get around it or sign problem-free. This has been tremendous. And obviously, ALF has been instrumental, right, to this success. And one could expect this to go on and go strong and go on. The focus of our community has been on the sign problem, and to a large degree, rightly so, right? If it weren't for the sign problem, we'd be able to do so much more in exact fashion. This paper has been cited over 1,000 times. I haven't really studied this list, but of course, I'm familiar with the paper. I would speculate if you study the list of how it's cited, most of the citations are superficial. They're in the same spirit to say, okay, well, there's a sign problem, and therefore you shouldn't really, especially, you know, when new methods come up, this is the way to dismiss QMC.
Yeah, I would say Uwe is not happy with how it has been cited at all.
And the paper, so now when you discuss these things, it's always controversial. It can be easily misinterpreted what I intended to say, but this is our community. I just wanted to provoke some thoughts, right? How we do this. And some of the citations, I'm sure we contributed a lot to. Sometimes it's convenient when we want to say, there's a sign problem. I really don't want to explain to you what happened, but okay, that's a canonical citation because the most simple one. But it's had unintended consequences, I think. And the paper also, right, should be looked at in the right framework. The paper itself is correct. There's a couple of different caveats, right? One is the paper framed the sign problem very carefully. It says, if you do things this way, then there's the NP conjecture, right? But of course, there is a sign problem until there isn't a sign problem, right? If you formulate the thing differently, by definition, you won't have this problem anymore. If you found a symmetry, then it goes away, right? It's formulated as the usual way of saying, if you live with the sign problem, you already have a sign problem, you live with it, you sample it, you're going to have this complexity. But that doesn't, you know, we're seeing an increasing number of problems that become sign problem free under different formulations. And that caveat is, of course, often lost from outside. The second one, well, I mean, I think I don't want to beat on this too much because, again, it can be misconstrued as criticizing this paper. But I wanted more to bring this up as a discussion of how to correctly sort of balance a field's leading problem versus its potential for solving problems. So we may have, as I said this already, unintentionally enhanced the misconception. The sign problem just implies that QMC is not useful or shouldn't be used or not effective. And that's not true. One lesson, perhaps, to convince us, I want to draw is a different field that went a very different path. I think that has a similar problem to us. Many of you should be familiar with the history of density functional theory development. Of course, there's the Hohenberg-Kohn theorem, which led to the Nobel Prize to Kohn, that stated there's a universal functional. Okay. Well, the universal functional is not known, and all indications are, in order to find it, it's probably at least as difficult as the sign problem. Right? The two, in fact, could be coupled in the electron gas problem. But that field didn't, I mean, it dwelled on studying the functionals, but it didn't dwell, it didn't stop there. It didn't say, we have a problem, we should not apply density functional theory to materials. It went a different way. There's Kohn-Sham that thought about an approximation, right, using uniform electron gas. And now, of course, there's this commonly sort of thought of theory of the ladder, Jacob's ladder of DFT heaven, which is chemical accuracy. And you start with the local density approximation, you apply gradients and so on and so forth. And you leave Hartree-Fock theory, right? And then you go up. And this is widely spread. Some of you young people probably don't realize how big a field this is. This is citations as a function of time. Early days DFT, and then this paper was done a while ago, and I'm too lazy to go study this, but I am quite sure this exponential growth has continued. So if you look at this, you realize this is per year 14,000 papers, and I'm also quite sure it's undercut. This is an enormous field that propagates from physics to chemistry to biology to material science. And of course, you could trash DFT, we all do. But it's done many, many useful things, right? It's helped to make many, many predictions. It's in chemistry, in drug design, it's helped people actually make useful discoveries. But that difference, right, could have made all the difference. You could go on obsessing with locating this functional, right? Then this wouldn't have followed, I conjecture. So it's a different approach that that field took. It took sort of, I don't know, a balanced approach between development and applications. And it made approximations that target practical convergence. For example, chemical accuracy, which is a certifiable convergence, right? You're not exact, but you get to a certain level where you can make reliable predictions in chemistry that a reaction would happen or not happen. And keep in mind, when we say we have exact calculations, everything is approximate, right? Sometimes there's the Chinese saying that you kept your sesame, but you lost your watermelon, right? That you make a Hamiltonian, the Hamiltonian itself threw out a lot, and then you solve the Hamiltonian exactly. Sometimes that's crucially valuable in physics. You lay down principles, but we got to keep in mind that it's always approximate, right? So it's a matter of making the right approximation. And that statement is offensive in QMC because we've worked so hard to keep it exact. But I'm just saying that balance, I think, is important now for the field. Now the field has grown so much. So I don't know what happened there, sorry. In order to unleash the full power of QMC, we want to sort of revisit this, right? That it's almost universal. We stay with this doctrine. And I think continuing this problem-free models and optimize, this is obviously very fruitful. You should continue. By all means, if there's a good problem that can be formulated this way, this is the desired way to go. Unfortunately, right, for most models, this is not the case. And sometimes making those models fall into this category will drop too much of that model. And the same, you lose the physics in tweaking the model. For ab initio computations in materials and quantum chemistry, this is almost impossible. The sign problem is always present there. And in fact, as I mentioned, it's a phase problem. So we then need to say, well, there is a sign problem, we're going to live with it. And we need to understand what happened and then define sort of what I'm going to outline is you define a constraint and you remove the exponential scaling of the sign problem, but you change your mindset. Now you deal with inexact calculations where there's a whole set of things you've got to do after your calculations, right? If you do exact calculations, the first part is a lot of work, but once you do that, you have a result, you feel like you've done your job as a computational physicist, the result stands, right? But for this, if you make an approximation, you have to think about afterwards what the results might mean. Sometimes it's not accurate enough, right? But you need to adjust that mindset. So the idea would be to, I'm going to show you how this works, and this will help us understand the sign problem and then define the constraint. And then you implement the constraint. The idea would be with a trial wave function or trial density matrix in terms of what you already know with the AFQMC calculations. And then there's a newer ingredient where you can iterate this self-consistently. This is not something went wrong here. Okay, so I'm going to now go in a little bit more, talking about understanding the sign problem and then introducing this in the finite temperature framework. Okay. Questions so far? Okay, so the BSS algorithm, by now you're very familiar with. You write the partition function in this form where it's trotterized, and you want to compute observables. The observables are written so the main thing is we take the many-body Hamiltonian, and here, for example, think about Hubbard, where you've coded and so on. I'm just going to use this So the symbolic representation where after you do the Hubbard-Stravich transformation, you can write this many-body propagator as one-body propagators. So quadratic operators, which are functions of fields, and you have to integrate over fields. I wrote explicitly as a sum, so think Hirsch fields, Ising fields. And then you have this formula, you plug this in over these different fields, and then you have to integrate over the fields. Right? So basically each Bx, the field, is a matrix. Think about the field, this propagator, sorry, as a matrix, which is a function of these fields. And the matrix is of size ns, the size of your system, in Peter's notation, V, volume times volume matrix. And then you evaluate the trace, you end up with this, this expression that you're familiar with, and then you do Monte Carlo, you sample the fields, you do Monte Carlo to compute the sum. And of course, you know the symptom as temperature lowers, the average sign of this determinant goes to 0 exponentially, or as you grow the volume, it increases. So basically, so that's the finite temperature formalism determinant of 1 plus these products, right? Just stay with this picture. And later, we're going to come to finite temperature. Zero temperature. What you need to think about is that you have an initial trial wave function, and the initial function has the dimension of the volume of the system times the number of particles. You work with fixed number of particles, you do a projector, and then the whole thing, right, eventually what you compute is this form of the trial wave function dagger, and then this product. Okay, and for ground state, you want to make this path long enough, right, to converge. Okay, so I'm going to take this finite temperature thing now, undo it, carry out some Gedanken experiment to think about how the sign problem happens. Okay, so this is the original form, the partition function, and this is, if you could evaluate it, it's a number. And it's a positive number for no loss of generality. And this is the thing we just talked about. The propagator can be thought of that form. So I'm going to carry out this Gedanken experiment where I'm going to unroll each time slice systematically, time by time, going from the right to left. There's a symmetry. It's a loop, right? But I'm just picking one time and I'm going to start unrolling this. So if I unroll the first one, e to the minus tau h, plug this in, I get the second line, this expression. So Bx1, 1 now is a time index. So then this x1, and this is the n by n matrix we're talking about. So I'm going to call this quantity P1 of x1. It's a function of x1. This integrand, we're supposed to just integrate over one slice. The rest, I pretend I know. I could keep doing this. Now I could unroll a second slice. Now this will be an integral over 2 slices, the rest of them known. And I'm going to call this P2, which is a function of x1 and x2, and so on. Until eventually I unroll all of these, I get back what we were talking about before. Right? Question?
I'm finding myself a little confused between the operators and the matrices within the trace. Could you help me understand how to think of that?
So these are operators, and this is also an operator. B is also an operator. So every form here involves operators.
Okay, so this is the operator form, right. But then you at the very end,
and written it at the very end, this becomes so when you unroll this, you still have these operators, but when you do this, the last line, it's a matrix form. Okay. And I'm going to toggle back and forth between these two forms, but one is supposed to think of this as computing these things with the right operators.
Sounds good.
We also have a question.
Yeah.
Okay.
Question on Zoom?
Yes, I have a question. That's
Yeah.
on the previous page. You have a matrix labeled with X,
Mhm.
and if I remember correctly, it should be the luxury field or the time operator. I mean, it should be time evolution operator and labeled with X, right? So
Yes.
it is BX in this page. If I'm
Yes.
not understand.
So the x's, the little x's always have a time index. And on the previous page, so this capital X denotes all of them. It's a vector of x1, x2, all the way to xl. There are L time slices.
Okay, thank you.
Right. Or, sorry, in this, if I write one matrix, this is supposed to be x1. That's x2. Sorry. Yeah, no, you're right. I see what you're saying. You're saying I wrote them to imply that the x's are the same. No, sorry, I didn't mean that. They're not the same. There should be an index. Okay, so this is symbolic. So every matrix should get its own index, its own set of x's, x1, x2, and so on. Yes, standard BSS. I'm just sort of doing a Gedanken experiment to think about how I come from the beginning to this final form, which now is a function, right? Function of fields. How we went from operator to this. Now, suppose we know e to the minus tau h. What I mean is in this process, whenever I need to evaluate this function, right? This is now a function. If I could evaluate the trace, I'm going to pretend I could. Every step of these trace, I could evaluate. In other words, this is obviously, it's Gedanken, it's unrealistic. If you knew how to evaluate this, you would also know how to evaluate these x's too. But I'm pretending that I want to think about it this way. So in other words, I know how to evaluate all of these things. So suppose we know this, then I want to consider this sequence of p's. Now, I label these as capital L because operationally we have capital L slices. But I want you to think about capital L going to infinity, delta tau going to 0, and where's time step going to 0, in which case it's a continuous process, right? These things only change continuously. So, and I'm going to go from 0 to L to the left, just like sort of how we did here. And I'm going to monitor this PL. Now it's a continuous function, right? I start from Z, which is this P0, it's a number, because I know all of them. So I start from Z. I'm going to now depict this Gedanken experiment, this process, how the P's evolve. So I start from Z. It's one number. Now I'm going to introduce an x1. And x1 is random. So you can keep track of any possible x1s you want. In the case of Hirsch fields, you have 2 to the volume fields. And therefore, from here, there's 2 to the volume possible entries. And if you have a continuous field, it's a continuous distribution. So these values will differ from Z by a little bit continuously, okay, because delta tau is 0. So I'm just going to plot some typical paths. I plotted 2, one green, one black, for no reason. I just colored them, okay? But there are many. Now I go on, introduce BX2. So then it changes more. So the two path, the green one on the next step would be 2 to the volume, that many little branches. And so is the black one, right? I'm just picking another one, following it. And that's the green continuing. So out of the 2 to the V possible next steps, I picked one again. I'm just plotting a path. And this continues until I get to the end. I finish this process, and I hit this axis. And this will be these Monte Carlo possibilities that we sample. Our normal BSS is working on this axis, just moving each path, you move it around, you end up with a final value on the screen, right? My left-hand screen, it goes there. Okay, so far so good. You don't see the point, and that's okay. Why I'm sort of doing that, but that's okay if you follow me. Okay, good. So these paths, remember, they're growing. It's a fractal. They're growing exponentially large. It's a tree that's inverted, going left, right? There's a root, and then it grows exponentially. But any path I could follow, for example, this black one, it can be 0. But remember, I claimed I know all of these, so it could be exactly 0, and that's what happened here. So suppose it became 0. I want to ask, what does it mean? It became 0. Well, it means if you start from here, it's a root, just like starting from here. If I finish the rest of my Gedanken experiment, I have obviously an infinite number of paths. If I added those paths, so the future paths start from, so here is L, little l, and then L plus 1, L plus 2, all the way to L. If I started all the paths, and I've used 2 red ones to denote all the future ones, but there's an infinite number of them. They collectively would contribute 0 in Z by definition, because what you've done is so you're here, you have a particular choice of x1 and x2 that led to a P2, which is 0. Well, that means if you integrate all the future paths, you're going to get 0. Just by definition, you can get 0. So what this means is that for this point, from this point on, if I carried out with my quantum computer, I summed all the future paths, I would get exactly 0 in my partition function.
So your starting point is the high temperature, right?
Yes.
So it's T, yeah, so T infinity or beta 0. So so you're saying that the 0, when the black line touches the 0, that's basically like having a high temperature, which is 0.
So I have a fixed
because you said
temperature.
that you're sort of saying, let me start from this black line, when this black line touches the 0.
Yeah.
And so this is okay. So this you cannot argue with the high temperature. That won't work, right?
No, but it's not high temperature.
Any temperature
because-
works.
Yeah, sure.
Because you
So-
have the product of all the.
Yeah, I understand. Yeah.
This is
So
my
mathematically
temperature.
it works. I understand.
This is my T, inverse T,
all right.
1 over T. So whatever T, I could always break up your T into infinitesimal little steps, going from 0 to T. And I'm saying in that process, you could hit 0 because it's a continuous path. And that point is important, that I start positive. I have it's a random walk. I have some probability I will hit 0. If I don't hit 0, I don't worry about it. But I'm just saying, suppose it did, like this black line did. Then what happens? Okay, so this is the crucial thing. If you absorb this concept, the rest of the generalization to ground state or the other way around, everything follows. And what we do that ensues would make sense. So this is crucial. So if you have a 0, this says, by definition, the future will be 0. All the future paths, all the red ones, you should draw an infinite number of these, and each one will have branches. Starting from here, there'll also be branches. It's 0. And that just comes from this definition that P2 is 0. That means if I integrate out all the future slices, I get exactly 0.
So just, I'm struggling a little bit to understand the figure, the schematic. So the y-axis of this figure is the probability.
Yes.
So when you're saying hit 0, it just means the probability has become 0. So I would actually never pick the path if I knew the probabilities correctly. What does
it? When you have a sign problem, you do pick it up. You see that in your sampling. This connects to a subtle question that came up in Peter's talk. The reason you don't pick up the exact 0 is simply because when you sample, the normal way of dealing with the sign problem, you sample the absolute value, right? So you sample the absolute value of this. You sample absolute value of this object, PL. So the absolute value, there is a zero, but the zero, of course, is picked up with zero probability, right? But even if you examine all your path out of BSS, and at some point back in history, you look at it, you can get arbitrarily close to zero.
Yeah, I see.
Right? And I'm saying if you don't sample the whole path, you don't sample from the probability, you sample from, you just literally keep track of all the values, you are going to get zeros. In fact, you get plenty of zeros. You get many, many, many zeros in an unconstrained regular run. It's a pathology when you take the absolute value and sample it, you don't get zero.
I see.
You don't get strictly zero, but you get arbitrarily close. In fact, you get many, many paths that are very close to zero.
Okay.
I'm confused. So you said that PL is a probability?
PL is not a probability because it changes sign, but PL is the thing you want to integrate over.
So P0, which case are you considering here? First of all, is P I, is it a real number?
P, which one?
P whatever.
Yeah, all the P's for now, think about the Hubbard model. So they're all real, just to make our life a little easier.
Yeah.
Later, they can be complex, but for now, they're real, but they can be negative.
Okay, and so when P naught, let's say, starts out being positive, then you can think of it as a probability.
Yes.
And then
P naught, for any problem that we do, that let's stay with real auxiliary fields, the final partition function is positive. It's not negative, or for no loss of general. I mean, if it's negative, you just switch a sign, right? The final partition function is positive. So P0 is positive, but the path we produce are not all positive. And that we know from actual experience why the sign problem happens. We keep average sign, right? There are negative numbers. And I'm just saying, this is a particular way to examine. So in what we typically do, we don't do it this way. We just have a whole path. We wiggle the path, right? Like you did, you wiggle the path. And I'm just saying, if you examine the path history like this, you're going to see that it hits zero multiple times.
And I guess you'll talk about
and I broke time translational symmetry by insisting that we think about it from one time slice going to the final one, right? In principle, you could start from anywhere, but this is correct.
But you're going to talk about the general case when PIs are not strictly real in a second.
Yes, that would be more complicated. But the same understanding, this is crucial for dealing with that problem, which took another 10 years to deal with from here.
Can I also think of the figure in this way that let's say I have an auxiliary field configuration. And then within the BSS simulation, I know the weight.
Yes.
And in this case, the weight would be the value that you have to the very left. This would be the P at capital L.
That's right.
This is the weight of the configuration of the specific thing. Now I start, at least conceptually, I start integrating over all field values on the last time slice, but I keep all the rest fixed. And this will give me another number, and this is the number that you track. Just to the right of this. And you keep doing this, and in this case, let's say I follow the lower red one, which was a negative weight, so which was part of the sign problem. At some point, the red line meets the zero axis. So at this point, I know that all the fields that I can average over to the left will have to cancel. And if I was able to integrate over all the fields all the way to the right, then I end up with the partition function, the starting object that I wanted to know. And there I know that it's positive.
So so Johannes explained this well. So what we do in standard BSS would be we draw all these random paths that lead to values on the screen. And you're just sampling on the screen. So every point on the screen corresponds to a precise path that went from right to left. So all the fields are defined. They went, you don't care about what happened here. You're just saying, I have a value here. I'm going to sample them according to their absolute value. And then I keep a sign. When it's negative, it contributes a negative number. When it's positive, it contributes a positive number. But I sample on this axis. Each dot corresponds to an exact path that led from right to left, but you don't know the history. You don't care about the history. You just know you don't know about this value history, PL history. You do know the path positions, right? Because you've sampled them and you're updating them. So when you are here, this, if it's positive, you know kind of it's a good thing, but not really. I'm saying there are some positive ones that have contributed to the problem too. And if it's negative, we've grown all to dislike them because those are the negative weight things, and that's down here. But the origin of the problem dates back. And I'm saying, so how do you evaluate this value from your BSS algorithm? Well, you wouldn't be able to evaluate this very well because this value is the result of many, many paths that went from here to the future. So in principle, if you could do this thought experiment, you have a final thing. You need to trace them back. You need to group a lot of the final things together to trace back here.
Okay. So if I were, let's say, if I had the exact answer of what the P2 of X1, X2 is, then I could just sample these two variables and cancel everything, which corresponds to that final result.
That's right. So that's coming up in the last line that says, you know that if this is true at P2, this is 0. If P2 is 0, then all the future paths, the infinite number of them, would collectively contribute exactly 0. So then all the red paths would cancel.
Right.
So a complete path that successfully went from right to left would only contribute if the entire path stays positive. Because anytime it hits a 0, I don't care what it does in the future, it could be positive. But it's a part of this descendants from an ancestor that was at 1.0. So it's all part of a noise. So all the red ones are noise. So the only thing that contributed was the green. Okay.
But why would basically the rate of hitting a 0 not scale as large as basically you would have when you have a sign problem?
That's coming up next. So right now on this picture, it looks very innocent. It seems like it's very hard to hit a 0. Why would you have such a bad sign problem, is what you're asking me. So, okay, so let's establish these principles first, right? This is, so far, everything is rigorous and it's mathematical statements. What happened to the bad sign problem? Well, so the red ones, so when you have a sign problem, you know that for finite temperature, what's happening is you're integrating abstractly. This is now a path, an entire path that you sample. If you keep track of the final contributions, you're going to see some negatives. You're going to see some positives. And a bad sign problem means the positives are almost equal to the negatives. So when you integrate, you're looking for a little difference, and that's noisy. So the color is coordinated. All the red paths contribute to this patch. They cancel. Now the red path, the red color, does not mean that it's negative, as I said before. Just as much of it is positive. It went back, right? In fact, you could start doing all kinds of circles here. I don't care what you did. Once you cross a 0 once, you're permanently labeled red. And the future, you could do whatever you want. It's all part of the red. Okay. So why does the red portion grow? Well, it's a random walk. If you make this path longer, your probability, you're bound to hit the boundary at some point. As soon as you hit, you turn red. As soon as you hit, you turn red. So this probability might be small that the first time you hit it. This is why if you have a high temperature simulation, you don't have a sign problem. You don't hit it as much because you only traverse the short distance. But if you have a low temperature simulation, which means this is long, you just wait. The path will walk and sooner or later it'll hit. Once it hits, it turns. So by the time, if you move this to infinity, that's a 0 temperature, you're guaranteed everybody would have hit the path at some point, right? You're walking in this continuous space, you're going to hit that. So everybody would turn red, right? So the red proportion grows with the length. And that's the noise. So you're trying to salvage, you're trying to do this unconstrained random walk, trying to salvage a path that managed miraculously to escape from touching the boundary. And that's the signal. Well, that's why you have a sign problem, right? Because you're trying to rescue this a little bit. But once you understand this, it suggests a solution, right? You need to make sure that this stays above 0. You need to eliminate the contamination, the red. So you need to require not just the final one, stay positive. That would be like you do your simulation, you throw away the negative ones. We've all tried that, right? That doesn't work because that's random noise. But rather, you need to require P1 to be positive, P2 to be positive, all the way to be positive. In other words, you require the green.
Yeah.
Should you, this is an embarrassing detail, but should you not write this in terms of conditional probabilities?
Yes.
And then it will be much easier to understand?
Yes.
Thank you.
So that's coming up.
I'm sorry.
So you want all of this to be 0, and it eliminates all the noise paths, the dashed lines. In practice, of course, you don't know this because we were doing a Gedanken experiment, right? So in practice, you want to make this judgment with a trial density matrix. The trial density matrix would tell you that if you're here at the beginning, how much, is so you want the future evaluated. You want to know how much you've, whether when you touch 0. Okay, so here's the conditional probability. So how you realize this in a Monte Carlo sampling algorithm to incorporate the constraint. So step 0, you don't want to deal with the whole path, and some of you probably have guessed why. If you deal with the whole path, you cannot backtrack. If you get stuck somewhere with a 0, right, you have an ergodicity problem. And the probability, if you carry an infinitely long path, you go innocently sort of from one direction to the other, you hit a 0 is 1, right? So you're always going to get stuck. So that's why we undo it this way. You start with, so the red dots now mean, different color. The red dots just means, so imagine at the beginning, you set your field to 0, field value to 0. You haven't, they're all like the mean field value, right? The saddle point. Now the first step, so this is like one walker. I'm going to construct your path, but not with the metropolis, but with the random walk that went from right to left. So the first step, I'm going to propose to move one field. So P0, so this is our final PL. This is the thing you normally would sample in BSS. I'm writing it in this conditional set of probabilities. P0 times P1 over P0, P2 over P1. Now you notice that they all cancel, so you just get PL in the end. Right? So this is correct. You're sampling in the end PL. But you sample this through a procedure that starts from PL, which corresponds to this probability. It's just a number, right? And this number now, P0, is not the final partition function, but rather some mean field estimate of that. Right? You assign all the field to fixed values. Now you sample a P1 by doing this, P1 over P0. P0 is a constant, P1 is just Bx. The rest of them are with Bt. These are all with Bt, B trial. B trial is the mean field approximation to the sum over X. So you sample P1, you move this field. And now conditional on this field, you sample the next one, so P2 over P1. And you keep going until you've finished the whole path. So this is a departure from Metropolis. It uses a branching random walk. And this is an important concept that because we don't have the whole path. So I will later come to this and sort of remind you how integral equations can be sampled by branching random walks. So this does a branching random walk from 0 time to t time or beta time. Questions?
Again, I'm trying to make sure that I understand correctly what you were saying. So can I think of the figure that you are plotting as for the simplest case, let's say a single site Hubbard model where per time slice I have one field configuration.
Yeah.
And when you have the red dots, you are saying that the B matrices, this is the mean field approximation that I need to know to calculate the value of the path, or to calculate the average over the other fields all integrated. And now I start to release this constraint by saying that on the first time slice, I take out the mean field B and replace it by the Hubbard-Satonovich B.
Yeah.
And now I start moving the field a little bit by changing its value to something.
Yes.
And then still approximate I think now of all of these B minus e to the minus tau h as the mean field replacement.
Yes.
To approximate the weight of this integrated path.
So to build on what Johanna said, P1, in here, the Gedanken experiment, we can't calculate it. But in practice, how I would define P1 x1 would be its trace of BT, 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 BX1. And this BT, I could take this to be a mean field. Now, this corresponds to a single matrix with some fields that you fix. So this is just equal to determinant of I plus BT. Now a switch of, to be sure, these are operators, and this is also an operator, but now I can write the matrix. These are matrices. Okay. So generalize this P2, X2, X1 to be the same thing So basically, the BTs serve as importance functions. As you go from right to left, the BTs help you predict how important you're going to be.
Yeah.
But the conditional probability cancels in the end. No matter what these things are in the middle, the final thing I sample is correct. It's the final PL. Is the same as what you would sample in BSS, except I've gotten there through a conditional set of probabilities, and they won't alter. If these were all positive, I would have gotten the same thing, just with more noisy paths. But right now, because there are zeros, I would have gotten there with the boundary condition imposed, since I'm walking one direction. So anytime I hit a zero, the probability is eliminated.
Yeah. So and now let's say I have, I somehow managed to choose x1, and I'm in the step of choosing x2.
Yeah.
So what is the condition where I say this is a value of x2, which essentially represents to the path hitting a zero, so that I say, okay, this is a move that I reject, or how does this work?
Yes. So
and what's the condition on throwing the path away?
If you faithfully sample, so you've done this, you're sampling this.
Yeah.
If you faithfully sample this, it'll automatically reject a path that goes to zero continuously. It just makes the probability vanish at zero.
I see. I see. Okay.
And in reality, what we do in there is a force bias. It's an important sampling transformation that changes the field, that shifts the field. So when you're approaching zero, it shifts your sampling away from zero. And so the whole probability vanishes linearly at the node.
I see. So in the Monte Carlo, you would have, like in the classical BSS Monte Carlo, you would have the B axis everywhere, and then you compare two configurations, in the usual way.
Yeah.
And here I just have to think about this of the all the BTs or all the Bs to the left of the time where I'm at. I replace them by BT and then do the same ratio of determinants.
Exactly.
And when it's 0, I throw it away. I'm done, and I'm done.
It's almost
well, I'm not
identical
taking it in the first
when you,
place.
for example, when you're sampling P2 over P1, what you're doing is you have determinant of 1 plus. Now, BX2, BX1. So in normal BSS, you have a BX2 old, BX2 new.
Yeah.
You do this ratio. Here I have a BX2 old equals mean field.
Yeah.
Right? Or 0 or something. Yeah. But it's the same, you can see it's the exact same machinery. You'd be able to sample this. And this, of course, is non-negative. So you will not pick a X2 that violates the condition. And this carries on.
So am I correct in thinking that at the beginning you're using these mean field Bs in order to see if you hit a 0 somewhere in your path?
Yeah.
Once you get to the end though, and you don't have the mean field anymore, you could still end up with some negative
No, I'm done.
determinants.
When I get to the end, all these fields are fields I'm happy with, because on their way here, from X1 all the way to construct this whole path, I've never violated the path condition. So that's one of my green paths. And I'm going to compute properties based on this. Yeah. So I constructed this path going this way.
But with the approximation involved, you don't end up with, you're not guaranteed to have only the weights that would contribute at the end, right? You could get additional one. I mean, yeah, where does the difference happen due to an approximation, I suppose?
And the real thing.
Yeah.
It's enormous difference, because when I go here, every path, so on this picture, I've sampled this. The normal thing would sample this. So if you compare, if you ask, what is the probability that the final path that I give you, which is of course a large set, I can sample as many of them as I want. By the way you do this is you start from a population, 5,000 walkers, you do this, each one of them, you do this. And then you repeat this procedure n times, as many times as you want. So the final samples are 5,000, one set of 5,000 configurations, like in BSS, and then times n, how many times I repeat this. So if you ask, out of the 5,000 times n paths I end up, what is the probability that I would find them in the BSS sampling? The probability is essentially 0, right? Because it's this. The BSS is sampling this, the red, the whole thing, green and the red.
I guess my question is, at the end, when you have this determinant of all these B matrices that each have a specific, let's say, Hubbard-Stratanovich field, those are all exact weights from the full partition function that one would sample from before. So everything right now looks exact, but there's something that
under the condition that I produce the path without violating this condition, and these conditions are set up by the trial density. So every step, it's a conditional probability. Every step, this has to be greater than 0.
So if there was no sign problem, then these trials, the fact that you use them, it would just be like importance sampling.
Yes.
And it would just be exact but more noisy.
There's a caveat. If you use a single determinant trial, so for example, there's all kinds of sort of next level details you worry about. For example, if in these problems you use a projected BCS, in other words, if you have a strict 0, like a single mean field, as you go through this process, it'll still stop the random walk. This has to do with the question I was going to ask you. As you go this, if you have a 0, both sides are positive, right? When you have a sign problem free situation, this is positive, that's positive too, but there may be a 0. then this random walk, if you impose the strict condition of infinitesimal tau, it'll stop you at the 0. You won't sample the other side. You'll have an algorithmic problem, and you'll have a bias. So sign problem-free half-fitting case, you do this, you can have a biased answer. In fact, it's the most biased answer for the Hubbard model because the mean field is the most wrong at half-fitting versus other fitting. So what do you do? So all you need to do is you recognize you have a 0 where you got stuck. You just make the 0 not 0, slightly positive. It'll go through. It'll tunnel through. And then you could use 2 determinants that'll allow it to. Because when one determinant is 0, the other one is not, because it's a positive number. So that's also how we fix how we deal with the infinite variance problem.
So, I just wanted to understand okay, but so in the case when you will find you will hit the 0, like what is the, I guess, probability of finding it dependent on your trial density matrix? Like how hard do you have to search? How much do you have to change it to like how many trial wave functions do you have to try in general?
To do what?
To get an I guess to get an accurate result.
For each trial wave function, you have a final fixed answer. That answer is biased, right?
Yes.
So the rest goes into what I was saying earlier philosophically about if you have an approximate calculation, what do you do to understand the approximation? So yeah, we do different things. In chemistry, for example, we grow the number of determinants and we see that there's convergence. That's a good way to judge that it's converged. In here, I'm going to tell you about self-consistency that changes the trial wave function or trial density matrix, and you can see how its answer is evolving.
So you just need one good trial wave function that that doesn't give you anomalous results.
There's no, so the philosophy has to be there's no, so if I don't know the answer, I have no way of telling you it's the exact answer, right? Yeah. But I can, in my calculation, have internal signals that tell me this is a bad calculation, this is a good calculation. I have pretty good internal signals, and I have external signals where I intervene with the trial wave function form. But it's an approximate calculation.
Right. So you have to kind of develop internal consistency checks, and then also some kind of checks with the physical observables, I guess.
Yeah. Now, the problem I talked about at half-fitting, where you don't have a sign problem, that's an easy one. I would know. I would get the exact answer, right? So when you don't have a sign problem, you could do this and you would get the exact answer. Yeah. That's an easy check. But when you do have a sign problem, if you ask me, is this the exact answer? I wouldn't, I mean, in the most general case, I wouldn't know. There are many cases I would know because I could do release and I could see that converges. Right? But those are additional, more advanced technical things I won't talk about.
Yeah. So then one more quick question. Let's say I evaluate this P2 over P1, and in a sign problematic simulation overall, then this quantity can become negative.
Yes.
And I would throw it away or not take this update.
Yes.
If it becomes 0, then it's a little bit more tricky because on one hand, the 0 could be a 0 that actually goes negative. And then this is precisely this argument where I wouldn't want these parts.
No, so think about that as a Trotter error.
Yeah.
So you wouldn't land exactly on 0. If you land on 0, you should reject it.
Yeah.
But what happens in a
0 or a negative value,
both,
right?
Both. So that changes your Trotter error slightly because you could argue, well, in some ways, so the continuous walk would land exactly at 0. But if it's a discrete walk, you're here, next step, you're here. You're estimating there's a 0. You reject it.
Yeah.
But in principle, you could be here, you land here, you're still close enough to 0. So the next order algorithm would do that. It's called a mirror correction. You can actually just project that, okay, it's positive, but I know that you construct a mirror. It's like in E&M, when you have a mirror charge, you can make the probability vanish, or you can, E&M, you can make the potential vanish exactly at the boundary. Right? So that's the next order algorithm with a little extra cost. But typically, we just do this, and when you extrapolate with the Trotter error, it's exact.
Yeah. Because it could happen that with a finite Trotter step size,
Yes.
I end up with a positive path and I miss the 0 and I
Yes.
treat the path even
Yes.
though I should not have.
Yes,
Got
yes.
it.
So that correction, the mirror correction, basically reduces, if you're close and you have some probability of going negative, you try one more step, and that would linearly make the node vanish. Wow, nice catch.
I have again a simple question. Am I getting right that once we have a sum problem, this path integral exponential of beta Hamiltonian, it's exponential small number. But for the finite system that you simulate, it's not there, it's finite. So your trick, I mean, like this constraint path or this ratio trick, this incremental trick you use, is that, can I understand like that is a smart way of pick up those 1 minus exponential part of the path integral, which is small, but it's still finite, for finite size, and pick it up in a polynomial manner.
Yeah, you could, I would even make a stronger statement.
Yeah.
So we do.
Because those small part, as you said, contribute to the partition function. In this basis, you choose to sample, right?
We do, so there's different sequences of taking the limit of both infinite size and infinite length. But we do ground state calculations where the signal literally is 0.
Sure.
Right? But you still can pick out a fermionic part of that 0.
Yeah.
So so for finite temperature, it is small, but not 0. You're targeting that. But you're targeting more profoundly, you're reformulating your partition function or your ground state to pick out a fermionic component, right? The rest is noise. It's a bosonic thing. Bosonic in this weird field space that we're simulating.
Yeah, but I think what is really important is how much you have to put in to pick this up. And effort, you have to make sure this is polynomial, not exponential.
So once I put in this constraint, it's absolutely polynomial. That has no problem. Of course, at the cost that it's approximate. But I think it's not, thinking about it as trying to salvage the way I presented it, I guess, lead to that impression. Trying to salvage just the finite temperature, finite piece is not general enough, because most of the calculations we do are ground state calculations.
Sure.
So we want to target a reformulation, rewriting of the partition function so that the fermionic part is correct, under the right constraint.
Okay, yeah.
I don't know, how much time have I taken? How much time do we? 17 minutes. 17 minutes more. Okay, good.
Some little questions. So one is, I just don't understand why there is a symmetry between the 2 red lines.
The 2 red lines?
The 2 red lines. Right?
Because they're trying to represent the infinite number of lines that originate from here. So it's a segment of the line. Right? This part is
there's no symmetry. So there's no symmetry to cancel with each other. So the 0 it just means the point is 0. So
there is a symmetry in the sense that if you sum over all the possible paths, I just drew 2 symmetric lines to represent that there is an infinite number that can originate from here. If you integrate all of them, you strictly get 0. So there is a symmetry from them. I'm not saying they're identical, they're like x and minus x, but there is a symmetry between them, their contribution to the partition function, in that they contribute both positive and negative that cancel.
And then another question says, and there you use the BT, the travel function, the wave functions to as the approach. So I just wonder, since if we have a green line, then we have the weight, then I have the configuration of the x1 and the xl. Can we just use the largest weight as the new BT here to add a new travel function?
The new BT. So the BT is a collective property. It's not an individual. The largest weight in your BSS samples, you're going to discover, you're going to run into things that show up more or less. But if you look at an individual path, I guess it's easier to understand this in the ground state formalism. So if you do a ground state projection and you pick out some random paths and you look at the determinant, you formulate a variational wave function. And you say, how good is this variational wave function by my biggest weight walker? You're going to discover it's an awful, absolutely horrendous wave function. But because it's a Monte Carlo sample in high dimensional space, any individual thing is a large fluctuation away from the final collective result. So this BT, even though it's a mean field, as a constraint is much more effective than anything you pick out from the Monte Carlo sample.
Oh, okay. So,
the Monte Carlo sample is like randomly tilted by fields. Of course, I mean, if you do an infinite simulation, you could combine some of them and make good ones. And the self-consistency procedure I will tell you about is a way to synthesize that, to use a bunch of configurations to feed back into this.
Oh, so you can feed back to the
Yeah.
BT. You can change that in the.
Yeah.
Yeah. Okay. Thanks. Yeah.
In practice, like if it's hit 0 at P2, and you're saying that the conditional probability P2 over P1 should be 0.
Yeah.
Like you basically, but you need to figure that out from sampling.
No.
Is that true?
It's P2X, right? So whatever X you tell me, I could evaluate this, and I realize it's negative. So that
But
X will be rejected.
I mean, right. Okay, so it's for the exact sample that you
Yeah.
have.
So it's a branching random walk. I don't just reject that path. So this path goes here. I propose the next one that's negative. I throw away this whole thing. The history is gone. This whole path won't grow anymore. It'll just be, it won't make it to the finishing line. So it won't contribute to the measurement.
And if you see that actually P2 over P1 is slightly negative,
Yeah.
then you just know that your step size is too big. You cross 0.
You cross 0, I just reject it. But
Yeah.
as I say, there's a higher order algorithm where you understand, it's just think about it in the 0 time step limit. It's
Yeah.
cleaner. The theory is all at 0 time step limit. And then the rest is Trotter error. You can deal with that.
So assume that I knew the BT, that I had the exact BT, right?
Yeah.
And I do the procedure. If the domain of positive paths or positive configuration is not simply connected, I will build in an error.
You could.
In the formulation you have.
You could.
So
yes.
do we know this? Is it something, this is not the case generally, or is it?
Yes. So there's interesting understandings about tiling theorems about nodes in that. So and this is a subtle connection with here because those theorems are about wave function in configuration space. And basically they say that there's only 2 domains, a plus and minus. Yeah. So here we don't know that. The general argument is it'll be even more connected than that because the fields, the determinants you think about in the random walk are actually over-complete determinants, right? They all have overlaps. Your individual walkers, if you go along these paths and you pick any 2, they're not even orthogonal, right? They're overlapping determinants. So basically it's hard to build make little of pockets. And there are some basic symmetry arguments that would say that they can't be a smaller volume. It has to be half.
Okay.
Right? So you would have to cut it into zigzag pieces, and there's no obvious way to achieve that.
Okay.
Okay. So there's been sort of lots of benchmarks, but I'll show you since I showed you the finite temperature algorithm, I'll show you some finite temperature benchmarks just to give you an idea. This is work done by Yuanyao He, who is a former postdoc. So this, for example, is high temperature. It shows a comparison with DQMC or BSS at 2. So this is the Hubbard model, doped Hubbard model, at temperature of 2 and 5. And that's where you could still do the BSS algorithm. And what this is showing is energy versus, I think this is chemical potential horizontal axis. And you can see that there are 2 bundles of lines. There's this red, which is underlying here, and the sorry, I don't. Oh, red and green. You're supposed to compare. That's beta of 2, and you can see that you can't distinguish them. Right, the beta of 2. There's very little negative things. You can't distinguish them. And beta of 5 is this set of lines. You also can't distinguish them. The inset shows the relative error, and beta of 2, there's no relative error. But at beta of 5, you can make a relative error up to 0.3% or so on the energy. Okay. So this is the versus chemical potential, the average density, similar story, maybe 0.6 max error at beta of 5. I forgot what density this is. Oh, sorry, this is varying chemical potential. So it's a little 4x4 system. And this is correlation, your neighbor correlation, and spin-spin correlation. Same sort of story. Here's the bigger one. And you can make up to several % on the relative error at half fitting. And that's where, of course, I could just lift this node, it'll be exact, but that gives you a sense of where the maximum error is. And this is using a wavefront, a trial density matrix that's the poorest you can come up with, which is non-interactive. Right? It just turns off U. It just writes the kinetic energy part. And so this will be easily improved when you do a actual mean field. So this is now trying to go to low temperature, and I guess that's still the energy per site versus temperature now. Going to the right is 0 temperature. This is high temperature. And there are 2 curves, so several curves. There's the DQMC curve, which is the red, underlying red. You're going to see it's going all the way from up here, high temperature, all the way to here, where it stops. The sign problem is too much, it stops. And the blue curve is the constraint version. It connects all the way. There are a couple symbols here. One is the 0 temperature constraint path answer, which is this purple thing. And one is ED, it's a small system, which is the red symbol. And there are 2 versions. Yao showed this, measure A and measure B of the constraint version. Measure A, which incurs a bigger error, this green thing, is when you do this, you just go from right to left, you stop, and you make a measurement at the end. Measure B is you restore time symmetry by rotating, by making the measurements at different places and averaging them. And so the blue is more accurate. It tells you, well, it's a double win because you get more signals as you can average over the path, just like you would do in a Metropolis algorithm. And you get more statistics. You also get a more accurate answer by restoring the time symmetry. So this is the density for, I guess, tuning chemical potential. So the same sort of story. Now you can, as I mentioned, so that's using a non-interacting trial density matrix. You basically just ignore the interaction. So it looks horrendous, right? You wouldn't really want to try that, but still it gives you accuracy that sort of is smaller than a Trotter error if you use a more aggressive delta tau, right, of 0.05 or something. Probably you incur similar error. So the self-consistent algorithm does this. So you basically produce a mean field. You use it as a trial density matrix to carry out the constraint path version of the calculation. And then you feed this back. You carry out AFQMC calculation with the trial density matrix as the constraint. And then you solve for the Green's function. You obtain the Green's function from your QMC. You feed this back. And then you make a fake. You could use any mean field you want. You can even introduce terms that are not in your Hamiltonian, right? All I'm saying is produce me a density matrix that mimics what I see in QMC, right? So here we've just used the Hubbard model mean field, but we tune the interaction strength. And then we solve the mean field to minimize the difference with the QMC density matrix. We feed it back in, and we carry this, try the new mean field. And we repeat this until convergence. The convergence means that it's been minimized. We cannot make any more progress. And so this is an example of this. It's a Hubbard model, but on a cylinder. In other words, it's periodic in the short direction, and it's open in the long direction. And we're trying to look at spin correlations, so we induce some local antiferromagnetism. And the reason we're doing this geometry is because in ground state, there's good DMRG answer that we could compare with. So this breaks translational symmetry. The calculation is easier now. Instead of computing correlations, you just look at spin density, and you see if there's some order that results. So this is the same thing, but for 4×16. So this is 4, periodic. You close it as a cylinder, and it's open along the x direction. And you do a line cut to monitor the ensuing spin correlation. So this is what happens at high temperature. There's DQMC answer, BSS answer, the red with the error bar, and the green is the constraint answer. You can see that you induce antiferromagnetism, so it responds in a short range, and then there's no long range correlation. And it comes back because both sides have pinning, so it comes back. Now, unfortunately, this is where BSS stops. Right? The temperature is such that if you go down further, the sign problem can't run anymore. But now if you lower the temperature, this is what happens to beta of 10. You can see this zigzag showing up, right? And the zigzag means up, down, up, down. It's an antiferromagnetism. You lower it to beta of 20. Its color is not great, but it enhances. Beta of 30, it enhances. And now you notice that not only it enhances, there's a node. It goes down, up, down, and then nothing. 0, and then up, right? It has a phase slip. And that's shown in here in this whitish thing. So it has a phase up, down, and then there's a frustration. And beta of 50, it just enhances this. And now you put in the 0 temperature AFQMC constraint and DMRG, both answers are very close. Right? So it's gotten to the ground state at beta equal 50, and that's the correct answer. So it finds an effective U. We're doing the mean field by tuning a random U, right? We're targeting a U of whatever it is, 6. But the mean field U can be anything you want. In fact, as I said, you could even introduce superconductivity if you want, right? It's any mean field you can tie it to. So this is a more recent thing, finite temperature calculation, and you can recover from a wrong state. What this is showing is it's the same sort of thing. It's a benchmark, a line cut of the correlation, and this is the pattern. The final pattern looks like this. So it has domains, like negative domains. So this is after a stagger, it's the staggered spin. So this is up, down, and then there's a down, up, down, up, down, up. There's a phase slip, and then up, down again, and then down, up, down, up. Right? So it has, that's the final structure. But we start with the actual mean field for the targeted U, which is 8. So the actual mean field is wrong. It predicts a diagonal order, right? The stripe is not linear as in this pattern, but it's like this. The mean field, you can see the zigzag, right? And it has the wrong period. If you look at the mean field, initial mean field, it looks like that. The period is wrong, and it's a domain. It's very, very high spin, and then just 0. The final answer, the mean field calculation finds an optimal effective U of 2.6 compared to 8. The actual physical U is 8. So mean field grossly exaggerates the order, and the self-consistency procedure tells you that the mean field is overestimating by a lot. And it restores, it finds the vertical stripe, which is a different wavelength. Right? So this recovers from the, and the self-consistency, so this is a plot of the self-consistency search. The vertical axis is beta, horizontal axis is U. So we now allow the mean field to be performed at a temperature that's also fake, right? In other words, we're targeting a beta of 8, let's say, but the mean field can be happening at a beta of 5 if it wants to, and the U effective is also tuned. And you can see that we start out at beta U of 8, and the corresponding temperature, and then it sort of traverses, and the background shows the chi-squared, how different it is from the QMC, the mean field. So eventually, the chi-squared is lowered, it finds here, and that's the final answer.
Yeah, 1 minute.
Hmm?
Yeah, 1 minute.
1 minute. Maybe I should just stop here. I don't have a particular, yeah. So this is a good,
Oh, nice.
this is a good place to stop. I've told you we're sort of here now, and I'm going to give you an idea of ground state and reinforce some of the ideas. I know this probably feels a little rough, and we're going to visit ground state. Maybe it'll give a better sense and just tell you a little chemistry next time.
Okay, let's finish Shiwei's talk. And
Thank you.
I think we can have few questions, and yeah.
Nice interception. That's a point guard. Or defensive advantage.
Well, that's the danger of having that. For your trial wave functions, I guess, yeah, and related to the U effective, what do you actually mean by U effective? Like, how do you measure it? And then also the trial wave functions,
so
yeah, I guess you can just put in the.
So let me just make Hubbard model, so this is easier. So there's a kinetic energy term, which is the hopping, and then there's a interaction term, and this has U and I up and I down. Let's just take the simplest case, and then there's some external potential that's pinning or something.
Yeah.
So if I do mean field, I'm gonna, say U and I up and I down. But I could say, I'm going to do mean field with some effective U. Tell me any U. I'm going to do this mean field and produce a trial density matrix.
Yeah, but then how do you measure it? You said that the actual effective one was different from the bare.
So I just scan. So if I have QMC results, I have CI dagger CJ. Let's say I have these density matrices.
That's all you measure. You don't measure the vertex
yeah.
function, right?
Yeah, you could do variance. We've tried different things, but basically the higher order statement is give me a mean field, which is now a function of U effective that will produce density matrices that minimize the difference with my QMC result. So search if you want. What we do actually in that last work we talked about, we actually have a grid at the beginning. We just compute all the different effective mean field answers. We store it, and then the QMC runs, we go search, and then we come back. You could do that, or in the ground state calculation, what we've done is actually couple the two codes. We run a QMC, we spit it out to a mean field code that does this, and then we send it back. Any operational procedure you like, it's fine. But the philosophy is simply hand me a mean field. And what I said before is this right now, we said it's Hubbard. It's like the physical Hamiltonian that you're targeting. You don't need to do that, right? You could add whatever term you want we haven't really done that, but you certainly could.
I guess the iterative procedure makes probably the most sense to me, the one where you don't care about what the form is. You just plug in the actual correlation function.
Yes.
As the next ansatz,
yes.
And you keep iterating over that.
So the philosophy is sort of made more firm because I broke symmetry, right? If I were doing a periodic system, this philosophy would be a little shaky because the mean field is breaking symmetry. How do I tie the two together? But right now I do a pinning. Like when I compute superconductivity, I actually have a superconducting inducing field, superconductivity inducing field. So then both calculations have an order parameter. I could match the order parameter. So then the theory is at least firm, right? It just says the best mean field that does this.
The pinning is only but the pinning is only at the edge. So you should do you restore the symmetry very far?
You restore the so the two
you have to find a temperature. So you know that even if you put the pinning at the edge, if your cylinder gets very long, in the center you should get SU2 symmetry again. Will you get that?
So
I mean that's will your BT basically only breaks the symmetries at the edge, or it breaks the symmetries everywhere?
So That's a great question. We don't, so now we're thinking about mean field at finite temperature, where it's a little bit shaky, sort of how so far what we've tried, the BT breaks symmetry, SU2 symmetry everywhere. And you could do more elaborate sort of things like what I call an AGP or something, a generalized Hartree thought, where you write a bigger density matrix, 2n by 2n, that has spin in there. We've not systematically sort of checked those. But so far, the trial things we use break that symmetry.
The pinning thing is also standard in DMRG, where it just
Yes,
the
yes.
edges of the system.
Yeah, so the idea, this idea is more firm in ground state, where you're developing order. So if you pin locally, the ordered system would go on forever once you induce it.
But the
right?
DMRG, at least what Stephen was showing, he has the ability of showing that if you put the wrong order at the edge, then it sort of disappears when you go into bulk.
Yes.
Right? So it wasn't,
Same thing
very,
here.
so here.
Yeah,
so same,
same thing
so
here. So you put you all try to do a local pinning, so you don't. But the superconductivity calculations, we actually put a global pinning. But you can do the global inducing field, and eventually when you extrapolate, you'll realize it's zero. It doesn't want to respond to it. You could do different responses. But for ground state, this is more firm because you have long-range order. You're trying to detect some true long-range order. So whether you put a local inducing field, the true long-range order will show up in the whole system as a constant, right, in zero temperature. And if it doesn't want to do that, it'll respond locally and then die off. And we see that very clearly. For finite temperature, what Thakur was asking, it's a little bit more, because the mean field is a little, the behavior is, I don't fully understand it, and we're still sort of trying to think about whether there's issues with the mean field messing. But so far, it looks quite robust. It just breaks.
I'd like to ask a question which is more aiming for the ground state physics.
Yeah.
So let's say I have a Hamiltonian that encodes a toric code with a topological ground state order. If I was to do this from in an auxiliary field, let's say a projective method, I cook up a trial wave function and then I project it with the full interacting Hamiltonian.
Yeah.
So even though for each snapshot of the auxiliary field, I always keep a Slater determinant, but I'm averaging over the field, so I can also mimic states that are not Slater determinants.
Yes.
Now, if you have this approximation here, where at some point you have to estimate what would be the weight if I was able to integrate over all the fields, but you replace this by the B matrix, which you said is a mean field matrix. Do I then not kind of restrict myself towards a Slater determinant, which might struggle with estimating the integrated weight and the zero, because I'm kind of missing
you could. So you don't have to restrict to a single determinant, right? You could, any ansatz of a linear combination of determinants is allowed and straightforward to implement. So in ground state, we frequently actually, so there are cases that relate to what you say, Johannes, that a single determinant just breaks some symmetry, but you know that the solution has to restore that symmetry. So you could write a linear combination of determinants that restore that symmetry and use that.
But that scales as the volume. The number of Slater determinants you would need to restore the symmetry will scale as the volume.
Yes.
So you have to, so that will, so how does that?
Unless, so there are symmetry restoring operators that can be evaluated faster than that, right? So there are integration over one body operators, for example, you could do that. In chemistry, we've done sort of at least restore a symmetry without the full solution in a shell or something. You need to restore that. In some cases, you need to restore the symmetry. But even when you have a single determinant, right? So the cases I showed you at the very beginning, you have a non-interacting determinant that doesn't break symmetry. It certainly doesn't lock your solution into a single determinant. You're still averaging over many determinants, right? It's still a many-body solution. It's just the boundary condition, right? So there's no guarantee that, no limitation that a single determinant constraint always guarantees you have what chemists would argue as a single reference solution. That's not a statement, right? That's not true. But there are cases where it's too restrictive. and then you have to restore that. Now, in the most general case where you can't evaluate the symmetry restoration cheaply, you have a exponential growing number determinant, you cannot find a cheaper reduction, then yeah, we have a problem. But so far, it hasn't, you seem to be able to find surrogates that would do enough of a job, right, to be very accurate.
So going back to the main idea of the algorithm, if I have a set of BTs and they are badly chosen for my problem of interest, is the issue that I will get zeros and negatives in cases where I would not have those for the physical model of interest, or and also that maybe sometimes I don't get zeros and negatives that I would otherwise have for the model that I'm trying to target?
Okay, good question. So you never get negatives. So the calculation looks completely innocent, like a good computational calculation. It's polynomial scaling.
Yeah, but you're avoiding those negatives. But I'm saying those, maybe you're avoiding negatives that aren't true negatives.
Exactly. You can have false regions. You carve out some half of the region. Basically, half the region you need to sample. Right. The correct theory says you don't need to do both. You need to do one of two regions, and that carving is wrong.
Yeah.
If it's very wrong, your answer is very wrong.
Yeah, if it happens enough times.
But the computation doesn't tell you that in terms of negative signs.
Right. No, this is not a diagnostic. I completely agree. It's more of conceptually understanding why it goes wrong.
It does tell you. So when you compute it inside, the variance of the Hamiltonian would start to diverge. It would like push back at you. I really don't like this constraint, but you keep wanting me to follow it, so I'm following it. But the variance kind of blows up, right? So that's a good sign that in the calculation, you're going to start seeing like large fluctuations because it really tries to go there and then it gets killed. So that's one useful way to monitor things. And of course, ultimately, you need the external things. You need to try different ansatz to see, okay, am I really just locking it into a state that it doesn't want to be? So typically, having a few competing state ansatz would help, right? You try those.
Okay, further question? If no, then we end the session. Yeah.
I would have one more question if I can. Sorry.
Yes, please.
So I didn't want to ask, so you can be in time. Where you have shown those conditional probabilities, and oops, the battery will just go down. My question is that if there were no Trotter error, because of the discretization of time, then the way you use mean field approximations at the beginning wouldn't be exact. I mean, you said that at the end the PL restores the exact value.
Yes.
And I don't see why does it become an approximation. Is it because the Trotter error, or is it also because the mean?
No. So if you had no Trotter error, you would still be approximate. In fact, you would have faithfully executed my vision of the approximation. That's because the Trotter error, so you've stopped the path from touching the zeros that you define completely and rigorously. With Trotter error, you've just implemented it. The boundary is slightly fuzzy, and the order of how fuzzy it is Trotter error.
Yes.
And that's all, but the boundary is still there. So in one case with no Trotter error, you've precisely defined the boundary and you've executed the simulation respecting that boundary.
Yes.
In the second case, when you have a finite Trotter error, you've made that boundary slightly fuzzy on the order of, the remaining order of Trotter.
Yes.
But both cases, you are doing the simulation under these conditions. So it's both are approximate. And in fact, when you extrapolate the Trotter, you would get to the right approximate answer. And that you should always first do, right? You shouldn't, otherwise it's a cancellation of two errors, Trotter and the constraint error.
But if you have no Trotter error, then the remaining approximation is what? The mean field approximation of the B matrices, or?
Yeah. So it's probably better not to call it the mean field approximation. I use the mean field as an example, but some version of the trial density matrix, you've defined the boundary condition in your path space, and that's approximation. So the rest, by the end, you're done. You're sampling a probability that looks like the BSS, but it's subject to that boundary condition.
Okay. Thank you.
Yeah.
Okay. No furthermore, seems. And we can end this session.
Thank you.